guys, welcome back. We have our next lecture here from section 2.7, Elementary Matrices and the LU Factorization for matrices. This is a pretty simple idea. Elementary matrices are just a definition we'll talk about here in a second. And the LU factorization is a way to decompose a matrix into a couple different matrices, right? So the same way we decompose like the number 6 into factorization, 2 times 3, that's what we call a decomposition. We're going to use a particular process to decompose a matrix. We're going to restrict our attention to invertible matrices. So decompose an invertible matrix into, again, 2 separate matrices. But let's do these things in order. Prerequisites, we need to know elementary row operations, as always. Okay, and we need to be able to do some matrix arithmetic, so matrix algebra. Okay, and with that we can handle these two ideas. So the first one's a bit of a definition. So what is an elementary matrix? So an elementary matrix is going to be any matrix that you can obtain from the identity matrix, from an identity matrix, using exactly one elementary row operation, right? So let me give that to you. So an elementary matrix is any obtained via one elementary row operation on an identity matrix, so some IN. Okay, so as an example, let's say this is so this is I2. Let's say we decide to permute rows 1 and 2. That will of course give me this matrix. And so this is an elementary matrix, right? You can do the same thing with multiplication, adding, again, anything you can come up with that will take you from an identity matrix. This is I2, you could use I3, I4, I5. With exactly one elementary row operation, we'll give you an elementary matrix. Now, why do we care about these elementary matrices? Well, it has an interesting effect when used in multiplication with another matrix. So let's look at a quick example here. So let's take here we go. We'll take a pretty easy example. So let's say I have 1, 2, 3, 4. So here's a 2 by 2 matrix. And we'll perform a very easy row operation here. We'll permute rows 1 and 2. Will of course give me this matrix here, 3, 4, 1, 2. Okay, again, very trivial. Instead, let's do something else. What if I did that same elementary row operation to the identity matrix? Now this is going to create an elementary matrix, of course, because I'm obtaining it via exactly one elementary row operation. But this matrix that I get out, I'd like to multiply this times this matrix here. Okay, so again, I'm going to take this matrix, that's 0, 1, 1, 0, and I'm going to multiply that matrix times this matrix here, 1, 2, 3, 4, and let's see what we get. Okay, so again, 2 by 2, and I'm multiplying it by a 2 by 2. Well, the result's going to be a 2 by 2. And I'll multiply, again, it's first row, first column. Okay, it's for 1, 1, row 1, column 1, multiply row 1 times column 1. 0 times 1 plus 1 times 3 is 3. Okay, row 1, column 2, that's row 1 times column 2, so 0 times 2 plus 1 times 4 is 4. Okay, the row 2, column 1 entry, multiply row 2 times column 1, 1 times 1 plus 0 times 3 is 1. And the very last entry will be row 2 times column 2. 1 times 2 plus 0 times 4 is 2. And look at what we have. We got the same matrix as we did when we just applied the elementary row operation to our original matrix. So is this a cute little, exception? No. This is the rule, okay? In general, applying an elementary row operation to a matrix gives you the same result as if you apply that elementary row operation to the identity matrix, take the resulting matrix and multiply it times the original. Now, hopefully you're thinking, yeah, but why would I ever want to do that? It's just more steps, right? Why wouldn't I just use the original one? Well, the reason we may want to do this is, remember, this is not an equation, okay? There's no equal sign between these two things because they're not equal, but this is, okay? If I label these matrices, let's call this one A, this one B, I'll call that one E, then what I have down here is an actual equation that reads E times A equals B. And when I have an equation, what's possible that I can shuffle things around, right? In this particular case, if I assume E has an inverse, this gives me a new way to write matrix A. Matrix A can be written as the product of the inverse of E and B. And the last very fantastic thing about elementary matrices is they're all invertible. Every single elementary matrix is invertible. So this will always be the case. We'll always be able to shuffle these things around. Okay? So what am I going to use this for? I'm glad you asked. I'm going to use this to try to factor a matrix. Okay? Now, you can't think of this in the same way that you think about factorization for numbers, right? So if you talk about integers and factorization, we typically think of prime factorization. And again, integers do factor in a unique way over prime numbers and the integers. Okay? 12 is 2 squared times 3. 24 is 2 cubed times 3. And again, these are unique. It doesn't matter how you divide out the primes. Eventually you come up with the same answer for every one of these. Some of the numbers we don't really split very easily, like 5. 5 is prime. But it's important to remember that this is only prime because of the realm of numbers we're looking at, right? So when we're looking at the integers, 5 is prime because there are no two integers that multiply together to give you 5 except for 1 and 5. And technically that's the definition of indivisibility, but neither here nor there. Okay. But if I look at something like the complex numbers, well, 5 is no longer prime because 5 is equal to 1 plus 2i times 1 minus 2i. So even if you think about something as simple as just expanding the integers you're looking at to the complex numbers, or even the real numbers, right? Because 5 is equal to, I don't know, 3/19 times 95 thirds. It is, yeah. So again, I mean, this is also equal to 5. So this sort of idea of primality, once you start branching out into different types of numbers, different types of objects where your mathematics is taking place, it sort of falls apart. Okay? So we can't come up with a way to take a matrix A and split it into two unique matrices where that particular factorization is replicable by anyone who randomly splits it up on their own. That's just not going to happen. What we can do is something called LU factorization. Okay? I should point out there are more than one type of factorization for matrices. This is just the best. This is the one we're going to learn in this section. Okay, and all this really means is that I'm going to take some matrix A, and I'd like to write it as a product of some lower triangular matrix multiplied times some upper triangular matrix. Okay, that's why the L for lower triangular, U upper triangular. Okay, and that's all I'm actually going to do. Okay, this is the best I've got with this particular method. Now, how am I going to do this? Well, I'm going to use the process that I used for transforming A into row echelon form. Okay? The row echelon form matrices, you may have noticed, are upper triangular, so that's got to be at least part of it, right? But I'm going to have to restrict myself I'm going to have to restrict the elementary row operations I can use. Okay, I'm going to get into this in about 2 minutes, but I don't want to use permutation. Okay, so quick rules for LU factorization: no permutation. Okay, and no A sub ij, where I is greater than j. Okay, I don't want to add a multiple of any row to a row above it. I only want to add down, right? So I only want to add down. I never want to add up. Now, this is really difficult now, right? Because with just, if I take out these, which is basically half of my elementary row operations, if I take out these, now it becomes very difficult to create actual row echelon form. It's not impossible, because of course we can always multiply to achieve the ones that we want to achieve in our pivot positions. But I don't want to do that, and we don't have to, because this factorization does not require a row echelon form matrix here. It only requires the matrix to be upper triangular, which means there's no requirement for those leading values to be ones. Okay? And in point of fact, when we work through this example that I'm going to work through in a second, I had no intention on creating ones. Okay? As such, I can actually do away, I could use it, but I'm not going to, I could do away with the multiplication elementary row operation as well. I'm going to be able to accomplish this no matter what matrix you hand me with only the add elementary row operation and only adding rows to rows below them. Okay, so let's get an example up here. I don't want to do a 2x2 example because it's a little bit trivial. So I'm going to do a 3x3 example so we can see how this process functions. I'm going to work it out the long way first, and then I'm going to show you guys, I will back up to the beginning, and I'll show you guys how quickly I would like for this to be able to be done. Okay, because really, I should be able to write, ideally, I should be able to do the row operations and then just write down the factorization from that. I don't want to have to do any extra work, but we're going to do it the first time. Okay, so let me get a practice matrix up here. I'll pull one out of the book because they're convenient and they've already been worked out. So here we go. We've got 2, 5, 3. So here's matrix A. A is 2, 5, 3. 3, 1, 2. Sorry, 3, 1, negative 2. And 1, negative 1, 2, 1. Okay. Always be very careful copying the stuff down on your paper, right? Okay, so remember, I just want this in upper triangular form. And so what that means is that I'd like to kill 3 of these values, specifically these 3, right? I'd like these 3 values to all be zeros. And if those are all zeros, I'm good. That's upper triangular. Yeah? And so what I'm going to do is I'm just not going to create ones in my pivot positions. Okay? I'm going to ask myself, well, what multiple of 2 added to 3 would give me 0? Well, if we think about it, that value is -3/2. Okay? 2 times -3/2 would give me -3. And if I take that -3 and add it to 3, that'll give me 0. So that's definitely one of the operations I want to do. Now notice I'm using fractions here, and that's not going to lead to some very nice numbers. But again, it's better than just multiplying the whole thing by half and then having, again, more fractions everywhere. We're going to try and do this in the minimum number of steps. Okay? How about A13? Well, again, what multiple of 2 added to this -1 will give me 0. And of course, that's +1/2, right? 2 times +1/2 gives me 1. 1 plus -1, that'll give me my 0. And that fixes my first column. Okay? Now, these rows don't interact with one another. This one changes row 2. That one changes row 3. I don't want to do more than that in just this one step. So let me go ahead and resolve that, and we'll see what we have. Row 1 doesn't change. So 2, 5, 3. Okay. Row 2. So we've got A12 -3/2. 2 times -3/2 plus 3 gives me 0. 5 times -3/2 is -15/2 plus 1 -13/2. 3 times -3/2 -9/2 minus 2 -13/2. Well, that's nice. Okay. Bottom row. So A13 1/2. That's 2 times 1/2 plus -1 is 0. 5 times 1/2 is 5/2. Plus 2 is 9/2. Okay. 3 times 1/2 is 3/2 plus 1 gives me 5/2. Okay. Now I'm almost done, right? This is the last value that I would like to zero out. And so again, I'm asking myself, what multiple of -13/2 added to 9/2 gives me 0? I know. That's not necessarily something that jumps out in your brain, but we can think about it this way. What I'd like to do here is, I'd like to figure out, what do I multiply 13/2 by to get -13/2 to get -9? Because if I can get -9/2, I can add that -9/2 to 9/2 to get 0. Well, I would argue this is clearly going to be a fraction, right? And now just look at the numbers and which ones you need and which ones you want to keep, right? I want a 9 in my numerator and a 2 in my denominator. I already have a 2 in my denominator, but I don't have a 9 in my numerator, so let me put a 9, right? And now I don't want this 13, do I? There's no 13 over here. So what if I put a 13 down here? And now if I do this multiplication, the 13s would cancel, giving me -9/2. So the multiple I'm looking for is 9/13, right? 9/13. So what I'm going to do here is I'm going to do A23 9/13. Okay, so I'm at 2, 5, 3. Row 1 doesn't change. Row 2 doesn't change. Okay, row 3, that's a 0. This one's a 0 by design. That's why we chose 9/13. And here I'm going to multiply, again, A23 9/13, so -13/2 times 9/13. That's -9/2. Add that to 5/2. -9/2 plus 5/2 is -4/2, which is -2. It came out pretty nice. Well, relatively. Okay, so let's discuss what it is that we know now. Okay, I'm going to label two of these matrices. Okay, this first one's A, And I'm going to call this last matrix U. Okay? I want this to be the upper triangular matrix in my factorization. The question is, where am I going to get my lower triangular matrix? Well, to that, I'm going to go back to what we learned at the very beginning of this lecture, which is that these elementary row operations can be represented as elementary matrices. Okay? In point of fact, this entire string of operations here can be represented with an equation, specifically this one. Okay? It can be represented as E3 times E2 times E1 times A equals U, where E1, E2, and E3 are the elementary matrices corresponding to A1, this row operation, that one, and then this one. So let me write those down. E1 would be the 3 by 3 elementary matrix where A12 negative 3 halves had been performed on the identity matrix. Well, what would A12 negative 3 halves do? Well, it would take row 1 and it would add a negative 3 halves right there. Yeah? Again, the first row is 1, 0, 0. Yeah, so it would be 1 times negative 3 halves plus the 0 that's already here. These make zeros. Yeah? So that's the only change. Now I want you to notice something. Where did the negative 3 halves go? What position? This is the 2, 1 position, right? A12 put that negative 3 halves in the 2, 1 position. And in general, A sub ij is going to put that value into position ji. So again, I don't have to work out E2 and E3. I can just write them down. E2 was created from A13 1 half. And so this is going to put a 1 half in the 3, 1 position. Right there. That's the 3, 1 position. Okay. E3 was created from A23 9/13, so it's going to put a 9/13 into the 3, 2 position. Fantastic. Okay? And so with these 5 matrices, A, U, E1, E2, E3, we now have this equation. This entire row operation can be represented with this equation. But the key here is that I can manipulate this equation. I know E1, E2, E3. I know these are all invertible. Yes? And so I can peel E3 off to the other side by multiplying by E3 inverse. You got to be very careful with the order with these things. Okay? As you can see, I've got to peel off E3 inverse first, then I can do E2 inverse, then E1 inverse, right? Yeah? And so what's going to happen on the other side, if you'll notice, is that you end up getting the reverse order for the inverse matrices. Now, in this particular case, it turns out we could shuffle these and you would get the same answer. But you don't want to do that in general, right? That's not true in general. Okay, so what do I have now? Okay, so I now have A, and it's written as a product of matrices. This isn't what I wanted though, right? I wanted to write A as L times U, something lower triangular times something upper triangular. I have the upper triangular part. But you know what? As long as that product is lower triangular, well, that gives me my factorization. So the question, of course, is, well, how exactly do we make sure it's lower triangular? Well, we did it already. the way you can make sure that this product is always lower triangular is by making sure that you don't use permutation and that you don't add a multiple of a row to a row above it. Okay? Well, this is fantastic, right? We already did that, so the product of these should come out lower triangular, but we need to figure out exactly what it is. Well, okay. In order to figure that out, I need the product of E1, E2, and E3 inverse. Of course, that means I have to find E1, E2, and E3 inverse. But again, elementary matrices are nice, and there's going to be a quick way to do this as well. I'm going to work out one of them directly here. So let me write what we currently have. I'll write this up here. So I know that's U, and I know from my work there that L is E1 inverse times E2 inverse times E3 inverse for my factorization. Okay. Let's take E1 and see if we can't find the E1 inverse. Now we know how to find inverses. What you do is you create this adjoint matrix. Okay. Where I have, I gotta put E1 on this side, where I put the matrix that I would like to invert on the left. It's almost the identity matrix. And on the right, I put the identity matrix. And then what I have to do is I have to apply elementary row operations to where the left-hand side looks like the identity matrix, which I should be able to do in one operation, because all I really need to do is take this one and kill that negative 3/2. Well, yeah, but the row operation to do that is just going to be A12 3/2, right? Because if this is value k, then the row operation would be A12 negative k. Okay? And that, of course, is going to give me the structure I'm looking for. That's going to give me this identity matrix on the left, but then on the right, applying that same elementary row operation, A12 3/2 to this right matrix, I get the following. So this matrix on the right, this is E1 inverse. But you'll note that E1 inverse looks really similar to E1. In point of fact, the only difference is that this non-diagonal entry changed signs, and that's true in general. Okay? So in general, the inverse for an elementary matrix created by the add elementary row operation, to invert it, you just swap the sign of the non-diagonal entry. Okay? Well, that's fantastic because it means I don't have to write this stuff out for E1, E2, and E3, right? What I can do is I can just take these and I can just write down what their inverses are. So here, we'll write down E1 inverse. That's 1, 0, 0. Instead of negative 3/2, I have positive 3/2. Okay. I should point out this does not work for other types of matrices, right? It doesn't even work for other types of elementary matrices. The only time this changing one sign works is for elementary matrices which were created by the add operation. Okay, so nothing else. Don't randomly do this for other matrices. E2 inverse. Let's see if we can do that without actually writing it down. So everything stays the same, but this 1/2 will become a negative 1/2. Okay, and last one, E3 inverse. Again, looking through here, here's my my non-diagonal entry, 9/13, and that's going to become negative 9/13. Okay. Okay. Okay, good, good. I'm almost done, right? I almost have L, because all I need to do now is I need to multiply E1 inverse times E2 inverse times E3 inverse. Well, I have to do them pairs at a time, so let me just do E1 inverse times E2 inverse. Let me do that over here. So I take E1 inverse, that's this matrix here, 1, 0, 0. 3/2, 1, 0. 0, 0, 1. I would like to multiply that by E2 inverse. Here's E2 inverse. 1, 0, 0, 0, 1, 0, and negative 1/2, 0, 1. Let's see what happens when we multiply these two things together. Because again, this is going to line up so very nicely. You're going to love the way this happens. Multiplying these two, let's see. It's 3 by 3 times a 3 by 3, so I know the result is going to be another 3 by 3. So let's just go by it one element at a time. 1, 1, that's row 1 times column 1. 1 times 1, 0 times 0, 0 times negative 1/2 is 1. Okay. 1, 2. Row 1, column 2, 1 times 0, 0 times 1, 0 times 0. 0. Row 1, column 3. 1 times 0, 0 times 0, 0 times 1. That's 0. Okay. 2, 1 entry. Row 2, column 1. 3/2 times 1 plus 1 times 0 plus 0 times negative 1/2. That's just 3/2. 2, 2. That's row 2, column 2. 3/2 times 0. 1 times 1. 0 times 0. That's just a 1. Next one, 3/2 times 0. 1 times 0. 0 times 1. Okay, 3, 1 entry, row 3, column 1, 0 times 1, 0 times 0, 1 times negative 1/2 is negative 1/2. 3, 2, row 3, column 2, 0 times 0, 0 times 1, 1 times 0, 0. 0 times 0, 0 times 0, 1 times 1, 1. And what happened? Did these non-trivial values here, did they even interact with one another? No, they didn't. And in point of fact, multiplying two matrices, two elementary matrices like these together, it's like the things overlap on transparency. If you remember back to high school, maybe your high school used transparencies, right? There's little clear sheets of paper you put on vinyl sheets you put on an overhead projector. If I just take this one and overlap it with that one, this is exactly what I would get. And that's exactly what's going to happen when I multiply this one in too, right? So again, multiplying in E3 negative 1, I know what's going to happen. It's going to put this negative 9/13 in that 3, 2 position. Well, that's fantastic, right? This gives me L, okay? Without actually having to do all that work. L is 1, 0, 0. Okay, it's lower triangular, and these values come from my inverse. 3/2, negative 1/2, negative 9/13. This gives me my factorization, right? This gives me my factorization. Now, I wrote a lot of extra stuff I didn't need, right? I know what L is, I know what U is. In reality, I should be able to write down the factorization from this step, right? I should be able to write down the factorization from this step. From this step, here's what I know. A is going to be L. L is going to be in this form. Oh, that's not a 0, that's a 1. U, that's the result of my elementary row operations over there. And the only thing I have to fill out now are these values that come from my elementary row operations, from my add operations, right? The first one is A12 negative 3/2. And I know that in L, right? So this is L, that's U. I know that in L, A12 negative 3/2 is going to put a positive 3/2 in the 2, 1 position, right? Because I'm going to invert it, right? All right, now I'm going to color code this so you guys can see where these things are going. Let me get red and green and blue, I guess. Okay. So this operation here A12 negative 3/2. Puts a positive 3/2 in my 2-1 position. Okay? This one, A13 positive 1/2. Okay? Is going to put a negative 1/2, again, change the sign, in the 3-1 position. And the last operation, A23 9/13 is going to put a negative 9/13 in the 3-2 position. So all the middle things I wrote are not really relevant. Okay, I don't have to do those. In point of fact, again, if you give me the matrix, I can put it in upper triangular form, not necessarily row echelon form, because those aren't ones, but I can put it in upper triangular form and then just read off what L is from the elementary row operations that I used. Okay, and ideally that's what I would like you guys to get to the point where you can do that. Right, I don't want you to have to go through all those middle operations. You should just be able to go directly here. Okay, all right, guys. As normal, there's homework. Please do it. Make sure you get some practice. I'll see you next time.